Hello lovers of chemistry, it's Chemicator, welcome back to my channel. In this episode, I'm gonna talk about protecting groups in organic synthesis and how they can affect the efficiency of a synthesis route. But before that, we should brush up on some basic concepts of organic synthesis. So let's start with a fundamental question. What is an ideal synthesis? According to Professor Wender's definition, an ideal or ultimate practical synthesis is generally regarded as one in which the target molecule is prepared from readily available, inexpensive starting materials in one step, safe, environmentally acceptable, and resource-effective operation that proceeds quickly in a quantitative yield. This definition clarifies why strategies such as cascade or multi-component reactions are so popular in modern organic synthesis. The reason is that such strategies enable multiple bond formations in just one step, increasing complexity while minimizing step count. If you want to know how cascade reactions actually work, check out this video to gain a deep understanding of this powerful strategy. Now let's explore how protecting groups impact a synthesis procedure. First, we need to understand why organic chemists use protecting groups. Imagine we want to modify one part of a molecule while keeping another part unchanged. Without protection, both parts may undergo reactions. So to ensure selective transformation, we protect the part we don't want to alter and manipulate the other part. The first obvious drawback is the increase in the number of steps required. In other words, protecting each functional group adds 2 extra steps to the total synthesis, one for protection and another for deprotection. According to Wender's definition, increasing steps reduces the efficiency of the overall process. Additionally, introducing and removing protecting groups leads to the material loss, as quantitative recovery is rarely possible. Another crucial factor in evaluating the efficiency of a synthesis method is atom economy. Usually atoms corresponding to the protecting groups don't appear in the final product, leading to an unfavorable impact on atom economy. Let's take a closer look at this concept. In 1991, Professor Trost introduced a set of guiding principles to assess the efficiency of chemical processes, known as atom economy. Based on this definition, it can be expressed quantitatively by dividing the molecular weight of a desired product by the molecular weight of all products. Notice that all reagents used, unwanted side products, and the desired product itself contribute to the denominator of this fraction. But what does this fraction really tell us about efficiency? Let's bring this theory into real-world examples. Hofmann elimination is a classic reaction in which a quaternary ammonium salt reacts with a base to produce an alkene. In this reaction, a tertiary amine along with water are considered as waste products. Now let's calculate the atom economy. Our desired product consists of 3 carbon atoms plus 6 hydrogen atoms, which gives us a molecular weight of 42.08 gram per mole. On the other side, the molecular weight of the waste products plus the alkene is equal to 190.21 gram per mole. According to the definition, atom economy is equal to 35.3%. For comparison, consider the Claisen rearrangement. As you can see in this reaction, there is no waste, and all atoms in the reactant are present in the final product. This is a powerful reaction because its atom economy is 100%. Now you have a clear understanding of why protecting groups decreases the efficiency of a reaction. In most cases, protecting groups are eliminated from the molecule, so they are not present in the final product, leading to a low atom economy. Notice that here I'm talking about ideal synthesis. This doesn't mean protecting groups are a bad thing we should always avoid. There are thousands of masterpieces that would be impossible to produce without using protecting groups. In the rest of the video, I'm gonna explore synthetic approaches that deliver the target molecule without using protecting groups. So let's dive into it. Hapalindole U and Ambiguine H are structurally related alkaloids derived from cyanobacteria. As you see, both structures have an indole core, and the only difference is the presence of a substitution at the alpha position of the indole skeleton in Ambiguine. To better understand the connections between atoms and bonds, let's take a look at the 3D model of Hapalindole. In this molecule, indole core fused to a 6-membered ring from 3 and 4 position. This 6-membered ring is further fused to another 6-membered ring. Notice that the two hydrogens at the joining point are opposite to each other, so the two 6-membered rings are joined in a trans configuration. In 2007, Baran's group introduced an interesting approach to synthesize these alkaloids without using protecting groups. The synthesis begins with this readily available and enantiopiure terpene, which should be joined to the free position of indole from the alpha position of the carbonyl group. This reaction is carried out by adding LHMDS as a base and copper too. In the first step, the base deprotonates both the indole and the carbonyl compound. Next, they are oxidized by copper to produce radical species. Joining the two radicals led to the desired product as a single diasteromer. In the following step, the indole should be joined to a bis carbon atom from its 4 position to form the 6-membered ring. The main challenge in this reaction is site-selectivity. The group used different acids to couple these two segments of the molecule via a Friedel-Crafts reaction, but all attempts failed to produce the desired product. Notice that this carbon-carbon bond can rotate freely. As a result, under Friedel-Crafts conditions, the 2 position of the indole participate in cyclization instead of the 4 position. The reason is the electronic effect of the nitrogen atom, which alters the reaction pathway and results in undesired side products. In this situation, the most common strategy is to protect the nitrogen atom to control the reactivity of its lone pair and direct the reaction toward the desired product by tuning the electronic properties of the indole. But the Baran group used an alternative strategy without employing protecting groups. They plan to use an indole substituted with a bromine atom at the 4 position. This precursor set the stage for intramolecular cyclization. It can proceed via radical coupling or a Heck-type reaction using palladium. The radical pathway led to the undesired 7-endotric cyclization along with debrominated products. Finally, it was discovered that use of Herrmann's catalyst as a palladium source and its slow addition were necessary to achieve a 65% isolated yield of annihilation product. Until now, the tetracyclic core of the Ambiguine and Hapalindole has been created. In the next step, this intermediate undergoes reductive amination to install an amine group in the axial position. After that, the crude amine reacts with formic acid to create a formamide, which is then converted to isocyanate using phosgene, completing the synthesis of Hapalindole U as a single diasteromer. The remaining steps are aimed at installing a tert-Prenyl group on the 2 position of the indole moiety. Before continuing to describe the pathway, let's explore some potential synthetic challenges. First, the isocyanate group is highly reactive to acid and transition metals, leading to the production of the side products. The second reactive group is the unprotected nitrogen atom of indole. Just like in the first step, it can change the reaction pathway, leading to the undesired products. Now let's see how Baran's group got around these challenges by using the right strategy. They used Danishefsky's protocol, in which the nucleophilic carbon atom in the isocyanate is chlorinated by tert-butyl OCl. This triggers a sequence of reactions in which the free position of indole attacks the nitrogen atom of the isocyanate, followed by addition of the prenyl 9-BBN as a prenylating reagent to the resulting imine. In the next step, the tert-Prenyl group should be added to the 2 position of indole. Here we face a stereochemistry issue, so let's take a look at the 3D model of this highly congested intermediate. As you see, the newly formed 5-membered ring is joined to a 6-membered ring from the left side, and another 6-membered ring from the upper side. This skeleton creates a folded architecture, in which the lower face is shielded by substitutions on the 6-membered ring. As a result, the tert-Prenyl group adds to the upper face of the imine bond due to steric hindrance. Irradiation of this intermediate leads to the Norrish type cleavage of the chloroimidates and initiates a complicated cascade of radical reactions, which affords the Ambiguine. After cleavage of the chloroimidate, this carbon-hydrogen bond undergoes homolytic cleavage to produce the Indole skeleton. After that, the lone pair of the nitrogen moves to the double bond, and the CCl bond attacks to the boron atom to liberate the 9 BBN from the molecule and produce the final product.